Hi, welcome back to the Statics Online Review session. In this session, you'll learn how to find an angle between forces in 3D. Um, in, in design, it's important to find two things. First, the angle between a force and another in 3D, here represented by theta. Or also, if you have a force in 3D and you have a line. Lines in 3D are always represented with unit vectors by finding the position vector and its magnitude. And if you need to find the component parallel to that line or find a perpendicular to that line, then we can use the dot product of vectors. So the first thing that we need just to review quickly, what is a dot product of vector? Dot product is a vector operation that is used to find this angle and also find the components of a force or parallel to a certain line in 3D. A dot product given by, and it's read by A dot B, or the dot product of these two vectors, is nothing more but the product of their magnitude multiplied by the cosine, the angle between them. So if we would use the angle, this angle, and need to find it, then we will just use the inverse cosine and then multiply by the dot product of the vector divided by the magnitude or the product of their magnitude. Before we continue, by definition, if we're using a cosine the angle, then obviously cosine 90 is 0. And that's why if we get the I, or the unit vector, or of the x, and dot the unit vector of the y-axis, will give you 0. And because a cosine 0 is 1, then we can get I dot I is 1. This will make it easier to find the magnitude of the dot product of these two vectors. So we just simply multiply the x component, or in that case here, because we I times I, and the j components and the k components, and then finally just add them together. The answer would be a magnitude, or just one number. It's not a Cartesian vector form. So whenever you need to find a dot product of two vectors, you need first to represent the vectors in Cartesian vector form, and it's x, y, z format, or I, j, k, and then multiply the x's, the y components, and the z components, and then add them together. So how we use that? If you find the parallel component of a force parallel to a certain parallel to a certain line in space, then we just simply multiply, because that line is nothing more but adjacent to that angle. Then we can just use the angle, cosine the angle multiplied by the magnitude of the force, gets you the magnitude of the component. Or the magnitude of the parallel component, it's nothing more but the dot product of the force and the unit vector that represent this line. So whenever you need to get a parallel, if you don't have the angle, then you need first to represent this line in unit vector by finding a position vector of 2 points that lies on that line, and then divided by its magnitude, which will give you the unit vector, and then finally get the dot product by multiplying the x's, the y's, and the z's, and then add them together. Uh, if we need to get the perpendicular component, so using the Pythagorean theorem, if the perpendicular is the opposite, and 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 the force itself, or the vector, is its hypotenuse, then the square root of this hypotenuse square minus the parallel component squared gets you the perpendicular component magnitude. So or if you need to represent it in vector form, is just subtract the x components minus the x component, and the y and the z gets you that perpendicular component in Cartesian vector form. Let's do a numerical example. In this example, we need to find the angle between that force and the line OA, here given by theta. And we need to find also the component projected. So the projected component, which means the projection of the force on the line OE, or the force parallel to the line OE. Notice that sometimes it's called the projection of the force on the line, or the force parallel, or the component parallel to that line. The information given are given by the force in Cartesian vector form, and also given the line point A coordinates, which will help us in representing this or finding the unit vector for that. So the first step is finding the angle. The angle, as based on the formula, is inverse cosine of the dot product of the two vectors divided by the product of their magnitudes. So which means that we need to have the two vectors. One vector is given, which is the force vector, 2i, 4j, and 10k, but we need to get the vector that represent this line. We can go with a position vector, we can simply to get from point O to point A by moving in this direction. So we move 2, positive 2i, and then we go in a positive direction of the y, positive 2j, and then we move in a negative direction of z minus 1k, 1m. So, or 1 meter, 1k. So, which means we can just write the position vector in this form: 2i, 2j, and minus 1k. You can go in any direction. You can write here 2j, 2i, and 2 and minus 1k. As long as you write it in this form, you're fine. So the following is finding that dot product, which is in that case would be f dot position vector ROA, which means that you just need to multiply 2 times 2 and 4 times 2 and 10 times negative 1. Please notice the negative sign, and the dot product will be 2 kilonewton meter. The following is finding the magnitudes of both. So finding the magnitude is the square root of the sum of squares of the xyz component of the force. So that's the magnitude of the force. And then the magnitude of the other vector here is the position vector. So the square root of sum of the squares of 2 and 2 and negative 1 gets you. So we have all the parts of this formula. Then we just can find the angle inverse cosine of that dot product divided by the product of their magnitude, which gives you the final answer for the theta, 86.51 degrees. Following, we need to find this component, the parallel component to the line OA. The parallel component is given by the formula that dot product of the force dot the vector UA. Notice here that we have to use the unit vector. In a previous step, we used just the position vector to find the angle, but for using that to find the force parallel to the line, you must use the unit vector and not the position vector. Please be careful with that, because many do the mistake in using the position vector in that step. You could use the unit vector also in finding the angle. So it doesn't matter, like if you need to find the angle, then the two vector can be represented by the force vector and the unit vector, or the position vector. But for finding the parallel, you must use the unit vector. So now we have the force vector from before. We have the magnitude, the position vector and its magnitude. Now we need to find the unit vector. The unit vector is given by the position vector of its magnitude, which means that I need to find 2 divided by 3 and 2 divided by 3 for the j, and negative 1 divided by 3 for. This is the unit vector of that line. You represent this line OA. Finally, just get the dot product of f dot unit vector OA, and this my multiplying 2 times 2/3 here, and then add to that 4 times 2/3, and then add 10 times negative 1/3, which is this term. This will give you finally the force, which is 667. That's the component of that force in Newton. Uh, Finally, or 0.667 in kilonewton. We could, because we have this angle, we could have just went with finding the a cosine alpha, because use that angle and using the force magnitude, in that case it's 1095 kilonewton, and then get the 68 degrees, and then in that case will be 0.667. So cosine the angle gives you that the component. In examples, if the angle is given, or it asks to find it first, then you can use it after. If the angle is not given, then you have to go with that form by getting the dot product of the force dot the unit vector of that line. Thank you, and see you in the next session.